Trigonometric problem. Now it's time to move on to motion. We already looked at the examples of the circular motion, but this time is more about circular motion. You're going to see that again, but something called harmonic motion is the main applications of this one. And unicircle, it was preparation to that. So we're going to introduce something slightly different. The trigonometric functions. So it still is a functions of not angles, but of numbers, real numbers. All right. Numbers rises in the context of where we live, and their dimensions, meters and things like that, is counted. But when you count 1 apples and 2 apples, I don't know, that number 1 doesn't have a dimension attached to it. That's one idea of understanding numbers in mathematics. There's no metric attached to it, right? So that's what I'm talking about, number. Just pure numbers, the location in the number line with no dimension attached to it. All right. Here, when it's an angle, we have degree attached to it, radian attached to it. And when we're using the angle in radian, we didn't write down the book. The website doesn't even write down that radian measure, so that they can easily mix these two things. So that's what we're about to enter, and it's about the motion. So let me use this little animation to motivate this thing. The first thing we're going to look at is a position function, and you see this a lot in calculus, in classical mechanics, and in all science starts from this position function. So your output is position and your input is something. Typically when you talk about position function, the starting point is a position function of time, like a t seconds. We talked about last time. Alright? So we're going to use the trigonometric functions to get the position of a certain thing. Alright, so let me use this animation. First, hide this one a little bit using this part right here, and then get this animation. Where is this? Oh, it's here. Somewhat it's moved. Make it smaller. Strange. Alright. Then I'm gonna hide it with this one. So I want you to forget about what you just saw, which was a circle or something. And this part, I want you to look at it here. This is, let's say, I'm going to sketch a picture first to explain this. All right. Suppose the situation like this. There's actually a little mesh in here, and there's a spring system, and all the way there's a ceiling like this. A spring, this mass is attached to the spring, and if you just let it sit there like 10 hours, it's not moving, but it is dealing with the gravity. So this is called equilibrium position. It's not moving at all. You hit it with a hammer or something, it begins to move. So it's moving up and down. You can imagine that motion, right? So just focus on the end of this mass, and this animation is supposed to show you that motion. So if I play it like this, and again, I'm not showing the spring and then all that, but just the end part of this is very slow motion. Okay? So this is going to be a position. This is a 0 position here, right? And after 1 second, where is this one? And if it is above, we're going to use a positive number to locate that position. Unit is not very important. Just we're going to focus on the magnitude, right? How the algebra work in the physics and engineering setting is they're dealing with a magnitude and think about units later. Units very important, but here just we're dealing with the magnitude. So that's the motion. Make sense? This is spring mesh system that you study a lot. So let me give you this idea of this function. So let's say the height ht is the height function of time t second in second. So according to our setup, and what is h of 0, you think? That was the equilibrium position. We set this thing to be 0. Anything above will have a positive height. Anything below will get a negative height, right? So we are setting this one to 0, right? It's relative. Okay? So, and after, let's see, if I'm setting this one back in here. So I want you to not focus on this circle, just this red dot part where the end part is. So this is supposed to be 0 and going to hit one positive sign. It's set as a 0.63. That means after 0.63 seconds later, the dot is over here, is shrinking. Maybe we'd hit it upward like this. So what do you think is roughly location is if this is a 0? And this is a y-axis in here. It's telling you that the height of this thing. Isn't that like roughly 0.6? Is that right? So I'm going to go back here. Write it down. Seems like after 0.6 seconds later, the height is a 0.6 centimeter above, something like that, right? And then I'm going to hit it one more time. Then it's 1.26. So what do you think the height is? Isn't that like a 0.95? Pretty close. This is a 0.9, I think. It's 0.95 and 1.26. So after 1.26 seconds later, it's like 0.95 unit above. Things like that. And then you can keep recording, and then we see the functional relation. Right? We see it exists, right? Correct? At given time, it's going to be somewhere. So there's a time and position relation. Whenever you see input and output relation, there is a function. Mathematicians say the function is defined. But when we usually look at a function, you look for formula so that you can answer this problem in the test, right? That's what we usually look for. What is the formula, right? I don't want to look at this experimental data. I want a clever formula so it predicts after, 1.9 seconds where it is and things like that. And that was Newton's task, right? Using this idea, they wanted to predict this position. So as far as I know, the person who first described the principle of what's going on here is this guy Hooke. I think is contemporary of Isaac Newton. And there is a pretty extensive literature about this hostile relationship between Hooke and Isaac Newton. And he said, he set out some principle. I'm not going into detail. But principle between its position and force is acting on it. Right? If you're over here in this position, and I can say something about what kind of force is acting on it, right? The physics is about the source of a force and what it does to the rest of the physical world that we can observe, right? That's the things that you do in physics. So he set out this principle. And Newton's secretly working on something called calculus, right? He was one of the inventor of a calculus. And Leibniz is another, is getting the credit, that another inventor at the same time. So Newton's was calculated, doing this more mathematically. So using Newton's calculus, and there was a mathematical deduction that can be made. That means it is not like we decided to use this function to model the position of this spring mass system. Mathematically, they deduce if the principle is accurate, there's nothing else. It has to be this formula. That's what I mean by mathematical deduction. And from there, and we can conclude, is a trigonometry. So if you go into the more detail of this statement, it reveals no nature whatsoever about trigonometry, the lowly triangle. And this Newton's idea of a calculus and mathematical calculation says it has no choice, has to be trigonometric function. So this connection, to me, this is amazing. It's just like Really, really interesting idea. So you're going to learn this in differential equation. After you take a calculus 2 and you're eligible to take the differential equation, you must, if you're interested in science and you must mathematics, you must take this differential equation too, and you will see how this has come about, what this mathematical deduction is, and you understand this amazing the connection. So I'm revealing it in here, and so what is it got to do with the trigonometry? This is a unicircle, right? This is a unicircle. What is special about the unicircle? We talked about it last time. It's something about x and y coordinates, right? Right. X squared plus y squared is equal to 1, and that's one thing, right? So let me go back in here. I'm going to sketch it. But what other things was important about this? That's right. This coordinate x and y, and the unicircle. The x itself is cosine value. Y itself is the sine value. Important parameterization you're going to use forever while you're taking science courses and mathematics course. All right, that's what's special about it. And this one is suggesting is that there's actually this little boy spinning this little stone in here. That's a circular motion. There's no mystery to it, and everybody understood nicely, and we solved some problem to it. And suppose you didn't see this picture, and we have a little source of light that's giving the parallel sun ray, and this is actually shadow of this thing that is doing the circular motion. And there is this actual spring mass system attached to it. And then you're doing the same thing. Spring mass system is creating this motion, and there is this person circulating vertically like this in a constant angular speed, and there's a flashlight, it creates this shadow. And this idea, the Newton's calculus and Hooke's principle, is predicting the shadow of this circular motion and spring mass system is supposed to be exactly the same. That is the short summary of what you're going to be studying in the differential equation. It's an amazing calculation that you go through. All right, so big picture is a spring mass system. We don't see it. There's no circle in here, but we realize that the big picture is just like a fourth dimension, just like Einstein's talking about. This is actually a projection of some more two-dimensional motion. Then you only see one-dimensional motion in the spring mass system. All right, that's pretty cool. All right, so the height right here that you're looking at, the height here, where y coordinate is this height, right? Therefore, if I switch this one to t, not theta, and if I use this t radian, right, and then this y is, the height is really sine of t radian, right? If you make a connection of angle t radian with the time, then this becomes function, the position function of time, all right? So they decide, if this is true, then we have to introduce something like this, sine of t second. Okay? The sine value is really the height of this thing. All right, so this is a motivation. So here's a new definition. This is not like the definition of a trigonometric functions of all angles. Not that complicated. It's actually very simple, and at the same time it's a bit confusing. But think about what we just did. All right? This makes perfect sense. It's old definition, the sine of t radian. We know what this means, right? But how about new definition here, sine of t seconds? You can't put t seconds into trigonometry. It's about angles, right? But we just care about this magnitude. We want to use this value of sine as a height. So this is a nonsense. You can't plug in second in there, but we're going to give a meaning to this one. This means sine t radian. That's what physicists wanted to do. We want to use this amazing sine function to describe the spring mass system. All right? So if you plug in t seconds, we're going to view that as a t radian. The output value is a number anyway. We're going to use that magnitude. Mathematicians don't care about all this spring mass system. We just want this function idea. So they go like sine of t, nothing. Meaning that it doesn't have a dimension, just a pure real number. 5, not 5 radian, 5 degree, just 5, right? Sine t is going to be sine what? T radian. Does that make sense? Sine 5 now is viewed as, right, it's not sine 5 radian, it's just sine 5, the number. Then we're going to view that as a sine 5 radian. So that's the definition of trigonometric functions of real numbers. So see if we have that title here. There's our title. So I'm going to just use that rather than writing it here. There's our new definition. Trigonometric function of what? Numbers. Not angles, just numbers. Okay? Alright, so what do you know about sine of 3, for example? Roughly, don't touch your calculator. What do you know about sine of 3? Sine of 3 radian, right? Which is close to 3.14. Therefore, you think about the pi radian. Where is your pi radian? You go back to circle, right? Right, 180, almost 180. So what is the sine about? Y coordinate on the unit circle, right? So what is the y coordinate on the unit circle? At 180 degree, almost 0, right? So if you hit your calculator, if it's set to radian mode, you should be able to see that it's some close number close to 0. That's what we're looking at. This is not 3 radian, right? Just sine of 3, so that you can just deal with the magnitude that rises in the application. But mathematicians don't deal with these units. They just deal with the number and what is happening to that number, and you go through the sign. All right. Does this make sense? So we just define sine of t. T is a real number. Then the meaning of sine of t, cosine of t, tangent of t, those things. All right? It's completed. This means sine t, what? T radian. Now, right-hand side makes perfect sense. You know what that means, right? Sine t radian. And here, cosine t radian. And this is tangent t radian. Does that make sense? All right. So this is new notation given the functions, real numbers. Okay. Whenever you have a function, think about when you introduce a function, first thing they do is to plug in and calculate. So you know input and what to do with the output, know that. If I give you sine of 2, what are you going to do to calculate that? You're going to grab your calculator and you're going to hit sine of 2. That may be the procedure. But in your mind, you know what that means. You're going to go to 2 radian on the unit circle and read off x coordinate and y coordinate. That's something that we can conceptually do it, right? But you have to rely on a calculator. That's the procedure when you go through. Next thing they introduce is that what is the graph of this function, right? When we write down functions like this, y equals t squared, for example, like that, when t is a pure number, you know how the graph of this one looks like? Well, it's a parabola. You try all the value in the horizontal axis t and vertical axis y, and you plot 1,000 values around these small numbers, and you begin to shape when x coordinate and y coordinate. That's the next thing you do, right? Usually. So we're about to enter that, but they also introduce some properties this one have, and that's important. And it's going to be used, the sine and cosine and tangent is going to be used in all mechanical systems. And in the mathematical formulation, the mechanical system is algebra between these two things, right? So we want to know some algebraic property of this thing, this function. So there's the important algebraic identity. There we have learned algebraic identity. What identity do you know about sine, cosine, tangent? there's something called P identity, right? Pythagorean identity. Who remembers Pythagorean identity? That's the definition. It's not identity. Yeah, it is something that other property that satisfies. I want you to think about it like this: x squared plus y squared equals 1. If I write this one down, what do you think about it? What comes to your mind? Unicircle right away, right? What are these x and y? That's a cosine and sine itself, right? If I plug in cosine and sine there, that becomes an identity. So it's immediate now. Now the cosine theta squared, right? Isn't that the x-coordinate on the unicircle? And plus y-coordinate? Sine theta squared is equal to 1. That's immediate. How about that? Is that right? Yeah. So this is called what identity? Pythagorean identity. But it is properties algebraic, so it is a kind of algebraic identities. But this particular one has name Pythagorean identity. Right? There's another one that involves tangent. Anybody remember that version? Right. Right. Tangent theta. If you square that and plus 1, anybody know what happened? It was related to cosine, not quite. It's the reciprocal of cosine. That's correct. What is the name of the reciprocal of cosine? Secant, right? Secant theta squared. This is also called the Pythagorean identity. And once you have the first Pythagorean identity, which we proved because it's immediate from the circle definition equation, this one is easy. If you just divide both sides by cosine squared, then you arrive at it immediately. All right? I hope you see that. But this is two identities you're going to use a lot in physics and engineering and calculus at any higher mathematics course. They're going to torture you. Anything that you can't proceed, probably first thing you have to think about is this identity to overcome that tricky problems that you can encounter. Okay? And they got a little, lazy in terms of writing these things. They use this very confusing notation. They put that square inside in here. They write it like this. If you see things like this, it is not like cosine is squared and then multiplied by theta. This whole cosine theta quantity is squared, is abbreviated like this, right? For some reason, this causes a lot of confusion to students. I don't know exactly why, but once they use this notation, it confuses students a lot. But I'm explaining that what this means. Like this, they usually write it like this: secant square theta. So any literature, look up in the internet or books, they all write it like this, not with extra parentheses. All right. So I don't know if you remember, I briefly introduced this one actually back then, and I proved it in the general circle and not unicircle. So other identity they introduce is this even and odd properties. Okay. Now we introduce this sine and cosine as a function. So is an even and odd property is another thing. So let me actually grab it and copy this one, and they can see it easily. All right. Here's this thing called even and odd properties. The number is also called even and odd. The way that even and odd number behaves is very different from how the even and odd functions behave. Okay? So unfortunately, this is misleading. But they call this one. You probably have seen this even property, even function and odd functions. Have you learned those? Even function and odd function. Often is introduced in terms of a symmetry of the graph of this function. That's one way to understand how the even function and odd function looks like. But when you're mathematically establishing this property, you don't rely on rough shape. You have to actually rely on this algebraic calculation. Okay? So let's see, first one. Sine of a negative t is going to be negative of sine t. Seems like if you have negative inside the sine, this is not like sine is multiplied to negative, right? Sine is a procedure. If you reverse this procedure, we call inverse of sine. And when I introduce this inverse of sine, you probably remember that part. That is a complicated procedure, so you use a calculator. So that's why pulling this negative outside, negative like this, is a non-trivial matter. You have to explain it properly, right? There are a lot of functions like f of t, like this, and it is not necessarily equals to negative f of t. In general, this doesn't hold. Okay, you can't just pull out negative outside this seemingly complicated and potentially complicated procedure f. Right? The function usually represent procedure, can be very complicated. But sine has this property. If you have negative, you don't have to deal with a negative. Pull a negative outside, deal with a positive sign, and do the negative later. This is also described as order of operation. Negate first and go through sine versus go through sine first and negate later. Different order of operation. And there are a lot of examples that if you switch the order of operation, you end up at different result. Like putting your clothes on and socks, and that's okay, right? That order of operation doesn't matter, but inside the underwear and putting the jacket on, that order of operation really matters, right? So that's what we're talking about. In general, you can't just mix order of operation. But this one's true. Now how about this cosine? If you have cosine negative t, then it turns out this negative doesn't matter. It's the same as without the negative. All right? So you can imagine that you can switch the sine and cosine to, in general, f. If the function satisfies this type of property, it's called even or odd. This one is called odd function. And this one is called even function. When you accurately prove the function is even or odd, you have to establish this fact a little bit more carefully, not just looking at the graph of sine t, graph of cosine t. So I'm going to explain a little bit in here using the circle. It is defined on the circle, so if you have to establish the fundamental facts like this, there's no way you have to go back to the circle, rely on the geometry a little bit. All right? So let's think about small angle of circle to understand this. So this one picture does not represent all the situation where t is in the second quadrant and third quadrant. But if you understand this idea, and you can try other quadrants and understand what's happening there. So if I have this point right here in x comma y, and the unit circle x squared plus y squared equals 1, and if that's my positive angle t radian, but we don't write t radian, you can just use it as a t nothing, right? All right, so what is y and what is x? Sine of t, x here is cosine of t, unit circle, we know that. Now, this is right-hand side, sine t has appeared there, right? We look at it there. In the left-hand side, the angle is negative t, correct? So I want you to locate a negative t. If this is a t, where is negative t? Which quadrant? Let's say that was 15 degree. Where is your negative 15 degree? Fourth quadrant, right? So here's your fourth quadrant, and here I'm sketching it like this so that it triggers you, how this x and y changes. Would you believe that it's just right above, if you connect those two dots, it's a perpendicular to x-axis? Would you believe that? Knowing that, what would you say about the x-coordinate here? X-coordinate doesn't change, right? But y-coordinate will switch the sign. All right, this part is a bit confusing, so I want you to focus on this part in here. All right. We're looking at new angle, negative t, right? So I want you to calculate cosine of negative t first. What is cosine of negative t? The angle is negative t described it here. This is the terminal point. The x-coordinate of this terminal point is cosine of that angle, right? So cosine of negative t is the x-coordinate of the terminal point of that angle, which is x. Is that right? That's x right there. Let's apply the same principle to sine. Sine of negative t is that you go to the terminal point of angle negative t and read the y-coordinate, and that's going to be the value. Does that make sense? Not just y. So here is a negative y, because that's what you're looking at right there. That's where it goes. All right? All right, so, but we know about x and y. This is also related to sine and cosine of t. So what is y? Y itself is sine t there. How about x? X was a cosine t, where x and y are the x and y coordinates of angle t. So does that prove that no matter what your angle is, if it is as long as in the first quadrant, cosine of negative t will be exactly cosine t, and sine of negative t will be negative of sine t, right? The symmetry really goes along all around, and you can establish the fact for all the real numbers. Even 2015. Sine of negative 2015 is the same as negative sine 2015. So nobody knows which quadrant 2015 radian is, but it is going to be true. Right? All right, so we got this for free, and I was targeting sine, but we got this cosine as well. How about tangent? There's also important identity. Do you know how to write tangent in terms of sine and cosine? I think I've introduced one time, so it's reasonable. What is tangent? Y-coordinate divided by x-coordinate, right? Right? Y over... Isn't that right? That was the definition. Y divided by x. But in the unit circle, what is y? Sine t. What is x? Cosine t. So tangent t is always a sine t divided by a cosine t now. Right? Yeah. So let's see what happened with a tangent of negative t. Then you're going to stick in sine of negative t, cosine of negative t. Is that right? That's the meaning. What do you know about sine of negative t? Negative sine t. How about cosine of negative t? Cosine t. So can we pull out the negative outside? Then it remains sine divided by cosine, right? This is known as tangent t. So we can just write it tangent t. This is what happened. Sine tangent function is even or odd? Odd function, right? The tangent is odd. Well, if I give you a number, it's either even or odd, right? But a whole number, but function, there is a function that is neither even, neither odd, right? So here's a remark. Some functions are neither even nor odd. Sure indication it behaves different from numbers. All right, so that's a symmetry. So that's when Web of Science says shows, show do something, or when I say prove or show, this is the thing that I'm expecting. And if you just hit sine t in the calculator and looking at the graph, it's another thing that we should do, but this is the section in here. Trigonometric functions are real numbers, and there's this Pythagorean identity we just went about, and there's this even and odd properties on this fundamental trigonometric functions. Is that right? All right, next thing is a graph. I think I can do it here. Graphs. Right. These days we have these handheld calculators, and if you want a graph, boom, 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 you just get a graph. It's really good, and you have a phone, and you can get even a high-resolution graph and things like that. But I still believe knowing every corner of the graph of these fundamental functions really is important building blocks of your thinking skill in higher mathematics. If you rely too much on the technology and then not knowing about this fundamental property, I myself have a difficulty explaining why that hinders your thinking skill, developing of your thinking skill. But I'm a firm believer you better know this fundamental graph, just like y equals x squared and things like that. All right, so think about that, one doesn't know about the meaning of a slope, but constantly just, rely on calculator to sketch a straight line. It's very important that you understand the meaning of the geometry involved in the straight line. So this is like that. It's very, very important. And I'm going to show you another amazing fact about why the sine and cosine is so important. Not just for Spring-Mass Hooke's principle. Everything else, it turns out, sine and cosine is the answer. That's even a more amazing thing. All right, so here is our picture again. All right, so let me go back in here and use this idea to explain first a little bit about sine and cosine. What I'm trying right now is trying to sketch the graph of y equals sine of t, where t is a pure number. Okay, so I'm just going to erase this one a little bit. I'm going to rewrite it like this. This is where t is 0. Okay, and about that, here's a t equals 2, and here's t equals 4, and things like that. And we want to sketch, this is the real y-coordinate, right? Don't look at this as a y-coordinate. Okay, I'm going to plug in t equals 0 and plug in y value there. I'm going to plug in t equals 2, plug in y values there, and things like that. That's what I'm about to do. All right. So when t equals 0, let's say this is almost a 0 here. T equals 0. When t equals 0, it's a 0 radian. Is that right? 0 radian here. What is the y-coordinate there? That's what we're doing. What is the y-coordinate? Right here. 0, right? So at t equals 0, we're going to put solid 0 there. That's the point on there. All right? So what other special angle do you know? Like, let me go ahead and do this angle right here. I'm going to go and do that angle right there. What is the angle there? 45. But 45 is not, this is, secretly we think it's 45. But what is the right number? What is the t here? Not 1. It's pi over 4, right? That angle there is pi over 4 radian, right? And then we drop radian. Think of it as just a pi over 4. What kind of number is that, pi over 4? Is that 0.9? Can you do that for me, calculator? What is pi over 4? 0.7? Okay, 0.7. That's good enough. So this is 0, and that's 1 here, and that's roughly 0.7, and that goes a little bit up there. That's where is about roughly 0.7 is. But that is really coming from pi over 4. And then I sketched it wrong here. That height here, this is what we want, right? That's the y-coordinate there. Isn't that right? Translated exactly horizontally there. Okay? How about when t is over here? What do you know about that? What is the t value here? T value is not 0. X value is 0. That's interesting. Well, what is the t value? Y value is 1, right? And t value is, that's correct, pi over 2. Remember? T is representing the angle. All right? That's what t is. But what is pi over 2 roughly? Is that 1.52? I hope that's right. What is it? 1.5? Let's say it's 1.5. So here's 1 and here's roughly 1.5, right? So what is the value at there? Is roughly 1.5, which is really, I'm thinking, pi over 2. What is the y value here? Function value. This is the point that corresponds to that t radian, really. 1.5 radian is roughly 1.5 radian, right? And what is that function is capturing about that point? Y coordinate, right? So what is y coordinate there? 1. So you go up there, mark 1 there. This is almost 1 there. Is that right? And if you try more and more, like pi over 3 and pi over 6, if you try that, and you calculate this y value using the calculator, put it up there, or you can just vertical line is a slide it horizontally and put it up here. So you don't need a calculator. Just accurately sketch using the circle, and you can kind of roughly sketch the shape of the graph by putting 1,000 points in between in here. Does that make sense? So I choose a random t-value here and go think about how to calculate the sign of t-value. The y value is represented vertically or horizontally? Vertically there. That's the graph of y equals sine t. Okay? All right. So here's what you're going to do. When you sketch the graph of sine t, you think about a circle and focus on this vertical position. And you just rotate it. Rotate it like this. Right? So here's a shot. Here I'm about to actually sketch it. Y, and here's a t, and there's a graph of y equals sine t, right? Now think about the spring mass system again. So here is the initial position, right? As time goes, it goes up, and that's the part you have to remember. It go up and down like this, right? Isn't that the spring mass system? And that was supposed to be the shadow image, right, of the circle. That's exactly, this is the graph of a spring mass system. So have your pen and go up and down like this. That's the motion. But as you do that, you have to move your paper to the left or move actually your hand to the right. So I'm going up and down like this. I'm going up and down like that. That's the graph of a sine. Does that make sense? It starts, y coordinate starts with the lowest position there. So this is a graph. Okay, let's think about the initial position. This is where t equals 0. What is this highest height that you observe there? Right, it hits the highest points right there. And what is the t-value there? The angle, which is pi over 2, right? This is pi over 2. All right, and then it's coming back down. Think about the spring system. And it hits this position right there. Interesting. In the function, it's called x-intercept, right? But in this motion system, this is called equilibrium position. When it hits the equilibrium position again, when the height is 0, right? You keep rotating around. When is the height 0 again? Right there, right? When that angle is there. What is that angle there? Pi. So it hits the pi right there. What is pi here? T value is pi. Of course, x horizontal axis is x coordinate, but x coordinate is a different here. So I'm going to stick to t coordinate there. Is that all right? So do you know when it hits this lowest, the bottom, -1? What's the t value in here? I'm just going to keep going around in here. This is the lowest position vertically, right? And that's when it hits right there. So what is that value there? Another pi over 2 from pi, right? Here's where t equals pi. Another pi over 2 is a 3 pi over 2. Okay? And then it's coming back up and come back to the equilibrium position. All the way here. What is that value then? T equals 2 pi. Complete rotation. Alright? So sine starts at equilibrium position, go up and down and coming back to the equilibrium position. This motion is called one cycle. Right? You complete it. And then after that point, it repeats the exact same motion again and again. So what is this number roughly? 2 pi. 6.2 something, right? So it starts in here and go up and down and coming back up here and coming back to the equilibrium position. How long did it take to do that in this motion? After how many seconds later it completed one cycle? One cycle. What is one cycle? Going up and coming to the equilibrium position again and go below the equilibrium position, coming back up again. That's one cycle. How long did it take? 6.2 seconds roughly. 2 pi seconds is correct. Why is that? Because it was a shadow image of the circular motion, right? And this complete one cycle corresponds to one complete revolution. This motion. That's why. Okay? So actually air molecules in the air go back and forth like this to create this sound wave that we hear, right? And how fast go back and forth, how many cycles does it do that per second is hertz. And that idea is exactly the sine and cosine. It's very difficult to measure these, molecule movement, but the principle suggests that it must follow sine and cosine. Like a guitar string, plucking and going up and down, and it actually follows the sine and cosine motion. All right. So when you're asked to sketch one complete cycle of the graph of sine, then you start it here and end there and go a little bit further, just a tiny bit further, like this, and then put the arrow there, indicating it just continues like this forever, right? If there's no frictions from spring or from the air, then the spring mass system will go doing the perpetual motion forever if there's no drag forces involved. So go back like this. In mathematics, we don't care about beginning of the universe or anything. We just go to the left forever in mathematics, right? So this wave is forever in the graph, y equals sine t. That's the graph. So you truncate it here with a little bit of tag with the arrow is how you sketch the graph of sine t. All right? So I'm going to show you this animation finally. Now, I want you to see this dotted line. Do you see the connection of dotted line? That connection dotted line is translating the vertical height to over here to this graph of y equals sine t that we're about to look at here. So that goes like this. This is something that we sketch it up and down, right? And going in here like that. Because it started not exactly 0, that's why you're going over a lot more, 6.2, because it's shifted. But that's the graph of sine. All right? So if it moves like this, it creates sine graph. Horizontal is this angle measure expanded horizontally. Okay? But we use it as a time. And this is called what motion? Not circular motion. Circular motion projected onto the wall like that is called harmonic motion. Became very, very called simple harmonic motion. It's a very important idea. All right. So now let me challenge you with the next thing. All right. Let me do it here. Same space. Let's go to the next slide. I'm going to capture at least this thing. I'm going to save this. Just 1 second. Today is February 26th. All right, it's there. That's the graph, and let's practice. I'm hiding it. Maybe you're just going to flip to the next page, and let's practice sketching this one, right? So here, y equals sine t. Sketch the graph over sketch the graph of one cycle. Does that make sense? One cycle. So we're going to only look at a 0 to how many seconds? 6.2 seconds, better known as 2 pi, with a little bit of arrow at the end, right? That's what we're going to do. So I want you to do that. Also, if you can, I want you to be accurate with the scale. That's also something I'd emphasize at the beginning stage in here. So all the t. Start from 0 to where? All the way to the end. How many units? 6.2. 6.2. 6.2 is better information when you divide it, when you compare with 1. So here it's 2 pi, which is 6.2 roughly. And exactly half here will be pi, right? Remember what happened, those numbers? Those are the numbers that I focus on in here. Exactly half is a pi over 2. Exactly half was 3 pi over 2. Right? Alright. How about y? It goes up and down, right? What is the highest height? What was the unit circle, remember? No, the y coordinate. Where does it go up? It came from the unit circle. So what is the highest height? 1, right? So if it is a 2 pi, that's 1.5. So I think it's a little shorter here. So roughly about here is a 1 compared to pi over 2. Is that fair enough? That's a 1 unit correct scale to pi over 2. So I want you to be, that much accurate at least. It's going to hit that highest point and lowest point down here in -1, right? The motion is going up and down, but it expanded over, stretched over to 0 to 2 pi. Right? Let's try it. All right. I put it those 1, 2, 3, 4, 5 dots, right? Those are the easy coordinates you can calculate. So the graph must go through these points, right? Just nicely and smoothly, just like that ocean wave. Like this. And like that. And at the end, you continue a little bit. It goes extended like this to that extended. That's the graph. All right. I think it's really a lot like when you cross the x-axis there. It's a lot like a straight line. Don't do the curve too much. Straight line here when you x-intercept. Just try to curve it when you hit this top part. If you stick to that principle, it's easy to sketch it, and it's actually close to the real shape of the graph. Make it more look like just straight line, half of it, and then try to curve it. This is a graph of what? Y equals sine t, right? All right. So how long does it take to complete one cycle if it is like this? 6.2 seconds. That's the period. That's what it's called. All right. What do you think I'm going to do next? Number 1, I'm going to end this class. Number 2, I'm going to do something else. What is that something else? Y equals cosine t. Thank you. Yeah. All right. We're going to do the same idea. Where is that point on the circle? The beginning? It all the way to the 1, 0, right? 1, 0, and then it's going to go around the circle. So I'm going to do similar thing in here. See, this time I'm going to help you with the circle being sketched in here. We're going to look at the same thing. This time is x equals sine t. If I put x there, everybody said x should be horizontal axis, right? But is that okay? It's just a matter of labeling things, right? So vertical axis is now x here. What is horizontal axis? Always time, right? The time is this classical mechanical world. Everything is about time. So that's your input. And vertical represent whatever orientation of your displacement. Even if it is horizontal, that becomes vertical like this in the graph of a position function. Okay, so here's a circle. Here's our initial position, right? Okay, what is this supposed? At t equals 0, what is the x-coordinate? Isn't that, so y equals cosine t, I'm changing the y equals cosine t to x equals cosine t, right? X equals cosine t. So at t equals 0 is this position. What is the x-coordinate there? So we start from 1 here. That's the initial position. So that's 2 pi. And that's roughly pi. I'm comparing it with sine. All right. Who wants to go for pi over 2? Where is this point at pi over 2? Seconds later. Here, right? The point is over here, right? That's where t equals pi over 2. It's really angle, but it's pretended as if it is a second. So it's like a 1 radian per second, so it's here. What is the coordinate here? 0, 1. Which coordinate do you want? X-coordinate 0, right? But that number 0 is vertically represented here. That seems like confusing student a lot. The number 0 is vertically represented in the graph of position function. So here's a 0. Is that okay? X value is 0. X value 0 is not, that's not where X value is. This is t-axis, right? X value is represented vertically, x0 is down here. Does that make sense? Yeah. How about pi? Where is the point pi? It's over here, right? This is where t equals pi. But what are the coordinates? Negative 1, 0, right? Negative 1, 0. So what is the x-coordinate? Negative 1. But that x-coordinate is going vertical here, right? So here's down here is negative 1. Negative 1 down there. That's where the x vertically negative 1 goes. Is that right? How about 3 pi over 2? It's over here, right? This is where t equals 3 pi over 2, 270 degree. What is the coordinates here? 0, negative 1, right? What is the x-coordinate? 0. Again, this is not where x-coordinate is 0. X-coordinate 0 is here. Over the time, you have to put that number x vertically. 0. All right? Yeah. How about 2 pi? You come back here. X-coordinate is 1 again, right? So 2 pi, x-coordinate is 1 over there. So you have to somewhat go through this smoothly, and that one, it requires a little bit of work, so I'm just giving you the answer, that it turns out it looks just like this. Hook down there. So if you try more points, it reveals this shape. This is not sine t, I apologize. This is supposed to be cosine t here, x equals cosine t. Alright, what do you see? Imagine the sine t continues like that forever, and cosine t continues like that forever. It seems like there's some shifting relation going on here, right? So if I shift this y equals sine t to the left by pi over 2 units, do you see this becomes almost something like this? That's observation. If I shift this one about pi over 2 units to the left, then this one looks a lot like this one, shifting to the left. This observation is just an observation, but it is really the fact. By going through the circle, you can argue rigorously that it is the case. All right? So putting these numbers there, these numbers, t equals pi See, I think it's easy to remember these numbers, right? 2 pi is one complete cycle. What is the half of it? What is another half of it? What is the midpoint of that? Those are the 5 points that you have to put. And you think about where's the starting point. Sine starts at an equilibrium position, right? Go up and down, go through those marked points. And cosine starts at top, right? That's one thing you have to remember. And you go down, plunge, and come back up. All right? Think about it. Different motion. Not like here's an equivalent position. You hit it. So going up and down, you actually shrink it. Now you set the time clock and let that one go. Then it starts at the top position in here, right? And you release it. It passes through equilibrium position, go down, and come all the way back up. That's one cycle. It's a slightly delayed motion, right? But the phenomenon is kind of the same. So these two things really describing the same motion, slight time shift. But it's clearly different functions, sine t and cosine t. All right. Mock test will have this problem that says sketch the graph of sine t and cosine t over one cycle with all the reference points marked. What are those 5 reference points? 0, pi over 2, pi, 3 pi over 2, 2 pi. And you sketch it like this with this one additional thing I'm going to put in here. This I call this envelope line, amplitude line. Let me change that term this semester. Amplitude line, like that. This is you're supposed to sketch it. So, therefore, your graphing